Good afternoon, everyone. I'm really excited to be here at SysML today. I think this is a really interesting conference. I also realize this is the last talk of the day, so I hope you can handle one more PowerPoint presentation. I'd like to acknowledge my co-authors at the ARM ML Research Lab in Boston. And I'll start with some motivation for this work. So this slide shows a number of new sort of applications and use cases that have emerged over the last few years, and these are all driven by computer vision on mobile platforms, albeit quite different form factors. And these things all have sort of real-time performance requirements. So for instance, augmented reality on mobile, we need to keep the frame rate quite high so that as the user moves the phone around, the image displayed is nice and smooth. And on automotive, with sort of driver assistance, we obviously need to keep the object detection latency as low as possible so we can apply the brakes or whatever is required to avoid an accident. And of course, these things are also battery powered, and the impact of that can be different depending on the form factor, but it generally means we need energy efficiency. Okay, so I think improvements in computer vision is what's enabled these emerging applications, and we've sort of over time we've moved from the older-fashioned approaches like sort of handcrafted feature descriptors and SVMs towards what we often use now, like state-of-the-art convolutional neural networks. These are great; they're way more accurate than the older techniques, maybe 2.5 times more accurate. But they don't come for free. The challenge is the increase in the compute cost. So the y-axis on this plot that compares object detection algorithms shows tera operations per second, so that's the amount of compute workload we have to get done. And if we think about the sort of the power budget for a mobile device, maybe 1 watt, and the amount of compute we can do with 1 watt, you'll see that some of these state-of-the-art CNNs exceed that compute capability. So there's a gap here in terms of the performance and the energy efficiency on these devices. So how do we close this gap on our mobile platforms? So I think there's 2 things we can do. The first is we can design more efficient networks. So that usually means trying to optimize our network, not just for accuracy, but also for the amount of operations we have to do and the model size. I think we've made good progress in that. So example here, I think has been mentioned a few times today, is the mobile net architecture. It's quite widely used. We can actually do better than this now, and I think we're going to see some improvements there in the future too. On the hardware side, we can design more efficient hardware for neural network workloads. And there's lots of tricks here which I'm not going to describe. If you're interested in that, I'd recommend Ian Bratt's talk at HopChips last year, where he describes the ARM ML processor. But these are 2 things we can do, but we don't have to think about them as separate things. And I think, as in Ofer's keynote earlier, he mentioned co-designing, and that's very much something we think about as well. And that's kind of the approach we've tried to take in this paper, where we'd like to think at a system level about co-designing the network and the hardware that executes that network. Okay, so if we think about the hardware architectures that we use commonly today, say in your mobile phone, you typically have these different architectures. So we start with the CPU on the left here. This is kind of the workhorse in the system, and it tends to run the operating system and most of the application logic. And anything moving to the right is basically a specialized architecture. So a GPU was traditionally specialized for graphics workloads, and an NPU for neural networks. And the extreme of this is the sort of single function hardware accelerator. And we use this a lot for algorithms that are based around standards like video encoding and image encoding and wireless algorithms and these types of things. But it's a challenging thing because there's a very real risk of obsolescence in the hardware, because they basically do one thing well, but they literally only do one thing. So we've been trying to think in terms of sort of trying to achieve the efficiency advantage of single function hardware, but without losing the ability to sort of have flexibility and generalize to different data sets and different tasks. And one thing that we've taken inspiration from is transfer learning, so probably everybody here is pretty familiar with this. So, one view of this is if you plot the features you tend to learn in the early layers in a convolutional neural network, they tend to resemble something like this: Gabor filters, color blobs, textures, that kind of thing. And in fact, this paper from Jasinski, they basically make the remark in the paper, if you don't see these things, you've probably made a mistake. So that kind of shows that these are features that are generally useful for vision tasks. And we often use this in transfer learning, where we train a model on task A, and we transfer the weights to a new model, and we fine-tune the later layers in the model on task B. And this works really well. It means we can train more quickly, and if we don't have much data on task B, we can actually build better models. And kind of the punchline here is all around these features, so the fact that there's low-level CNN features that are useful across a variety of vision tasks. So the FixyNN architecture is an attempt to literally sort of encode that in hardware. So this diagram shows the neural network on the top and the hardware on the bottom. And we basically split the model into two parts. So the front-end part is a set of layers where we fix the model architecture and the weights in hardware. So they're fixed and they don't change. The back-end part of the model is different for each task that we want to execute. And it can have a different architecture and sort of arbitrary weights. The front end is fixed into hardware, so we have a fixed weight feature extractor part of the front end, and the back end classifiers run on a conventional programmable accelerator. The real benefit here in terms of energy efficiency comes from the fixed weight feature extractor. So let me talk a little bit about that. So the point here is we have a fixed architecture and weights, so we can apply a series of aggressive static optimizations. So they kind of fall into two camps. The first is data path optimizations. So here, one of the first things we can do is, because we know the weights in advance, we can actually prune any zero or small non-zero weights. So in a CNN layer, this can typically be around 50 to 70% of the weights can be pruned. So that removes an equivalent proportion of the hardware. Then if you consider this sort of long multiplication example on the right-hand slide here, we can also sort of prune the partial products as well. So we can do this because any zeros in the fixed multiplier basically always result in zero partial products, so we can remove the hardware for those as well. And then again, because we're accumulating less partial products at the end of the multiplication, we can actually optimize the precision of the result as well. And there's further things we can do as well. On the memory side, the weights are hard-coded in the logic, so there's no need to access DRAM memory to load them. And for the activations, because we have fully parallel hardware, we can actually pipeline the activations, and we only need to buffer a few rows of the output feature maps, rather than calculating the whole output feature maps before moving on to the next layer. The fundamental limitation here is chip area, because every time we add a parameter to the model, that adds some hardware in the feature extractor. Okay, and to help us explore this, we implemented a tool called DeepFreeze. This is basically a hardware generating backend for TensorFlow. So you give it a neural network model in TensorFlow, and you specify a set of layers, or the whole model, and it generates a hardware accelerator in Verilog, which you can implement for sort of ASIC or even FPGA. And we've open sourced that tool. Okay, so we want to evaluate the FixyNN architecture, and there's two main things they're interested in. One is the energy and latency improvements. And the second thing is the generalization, so the ability to use that fixed hardware across a range of tasks and data sets. Okay, so the methodology for this is to take a baseline, which is a conventional programmable CNN accelerator running MobileNet v1 network architecture. So this is not a fat model. This is a relatively efficient neural network. And we compare this against the FixyNN architecture, which consists of two parts: the fixed front end, which we model using DeepFreeze, and the programmable part, which we model using NVIDIA DLA. Okay, and we used 16 nanometer process technology, and we set the area constraint to be the same, so it's 3 millimeters squared. Okay, so as I said earlier, the real benefits come from the fixed weight feature extractor. So this slide gives some details on this part specifically, and the plots on the left show throughput and energy efficiency for each layer of the mobile net architecture. And you can see there's big improvements on both from the fixed versus the programmable accelerator. So in terms of throughput, there's around 8x benefit, and in terms of energy efficiency in TOPS per watt, there's around more than 68 times improvement. The plot on the right shows the cumulative circuit area as we fix an increasing number of layers. And this is kind of the fundamental limitation with this approach, which I alluded to earlier, which is that the area increases quite rapidly. The y-axis here is exponential. So for the Fixy architecture, one of the challenges is balancing the benefits of fixing more layers with the costs of higher chip area and the loss of generalization as we fix more of the model. Okay, so I'll try and start to pull together sort of more of a system level analysis here. So we start here with the baseline. The plot on the left shows throughput in tera operations per second as a function of area. And the plot on the right shows energy efficiency in tera operations per second per watt, also in terms of area on the x-axis. And here we have the baseline, which is NVIDIA DLA. So we have 6 different configurations of DLA. And you see the larger configurations actually result in good improvements in throughput, but the energy efficiency is relatively flat for the bigger configurations like E and F. So now if we add a fixed front end onto each of these 6 configurations, we get the orange line here. As you can see, for larger designs, adding the fixed feature extractor gives a good benefit, but there's actually an area for smaller designs where it doesn't really improve performance very much. Now, the orange line was for 4 fixed layers. We can add bigger fixed feature extractors. They add more area, but they also add more performance and increase the energy efficiency significantly. And this sort of gives a design space of choices, but in practice, for mobile platforms, the chip area is a very important constraint because it adds a lot of cost to the device. So we've imposed a sort of slightly arbitrary constraint of a 3 millimeters squared area. Okay, and we can then pick the best designs that have less than 3 millimeters square area. And here we've sort of cherry-picked a design that has high energy efficiency. So the throughput is similar to the baseline, actually, around 1.7 TOPS. But the energy efficiency is significantly better, around 22.7 TOPS per watt. This is around 3.8 times improvement in energy efficiency over the baseline. Okay, so that's improvements in the hardware, but that's only of use if we can actually use this hardware for a range of data sets that we're interested in. So to explore that, we trained the fixed weight feature extractor using ImageNet data, and then we fine-tuned the backend on 6 different tasks. So again, we use mobile net v1 architecture for this. So the plot on the right here shows those 6 transferred data sets in terms of the accuracy, and the bars show the number of layers that we fix, so fixing 0 layers is the baseline. And you can see most of these data sets are fairly flat on the top, which shows we can actually fix a lot of layers without degrading the accuracy. There were 2 outlier data sets which do drop off, and these actually are for data sets which have very specific images in, like aircraft or road signs. So for these networks, we're not actually able to maintain accuracy when we fix a large number of layers. So instead, we sort of fall back to just taking the activations from an earlier output in the fixed front end. So over the 4 of the 6 networks, we can use all 11 fixed layers, and we get energy improvement of 3.8 times. For those 2 slight outliers we studied, then we can still take the output after 4 layers and get a 50% energy efficiency improvement. And actually, what we haven't had time to do yet is to consider if there's actually a better methodology for training the fixed front end. I think that's quite an interesting research question, and certainly one for future work. Okay, so here's a summary of this paper. So I described how improvements in computer vision are driving new mobile computing applications, and there's an exploding compute requirement due to the move to bigger CNN models to get that accuracy. And this has led to an energy efficiency gap, especially on mobile battery-powered devices. FixyNN is a sort of first attempt to try and think about co-designing the neural network architecture in the hardware. The hardware consists of a front-end fixed-weight feature extractor and a back-end programmable accelerator. We then use sort of transfer learning to generalize that fixed front end to new data sets and tasks. And we showed up to 3.8 times energy efficiency improvement. And as I mentioned earlier, we've open sourced the tools for this, so if you're interested in playing around with this, please download that. Okay, that concludes my talk.
Good. Just one quick thing. If you're doing demos, can you please line up here?
So for your fixed part, did you try any specific regularization terms?
No, so for the fixed part, we didn't do anything special. We basically took a trained model.
So in your case, making parameters sparse is very critical, right, to reduce silicon area.
I'm sorry, can you repeat that?
Making your parameters sparse is very critical to reduce silicon area, right?
Yeah, so we just did a simple magnitude-based thresholding.
I think you should then try L1.
Yeah,
right?
so you can, I think I did make a remark, you can definitely do a lot better in terms of optimizing the model for the
So this
fixed.
is without any L1.
That's right, that's right.
So you looked at a variety of data sets for classification. Do you think this would hold for other types of computer vision tasks?
That's a good question, yeah. I was talking a lot about computer vision, but I kind of did a bait and switch and then talked about image classification. I don't know, I haven't really looked at that yet, but I guess some of those tasks, image classification is kind of like the basis for those, so possibly, but we need to do that, I think.
Thanks. All right, let's thank our speaker, and let's thank the speakers in this session. All right.